Rigid body analysis is the foundation of transient structural analysis. Hello, I'm Armin. In this video, we will learn how to model intermeshing gears using joints and contacts, and how to apply a joint load as an actuator. Before we begin, let me briefly explain the model. Let's get started. Rigid dynamics is a tool for analyzing the motion of a mechanism when deformation is not important. In other words, stiffness is ignored in the equations of motion, so the geometry does not require a volume mesh, and we focus only on the movement of the mechanism. A rigid body has 6 degrees of freedom, and this method uses the explicit dynamic solver, allowing us to simulate models over long durations efficiently. Rigid dynamics are widely used across many industries, but in this tutorial, I'll model 2 gears, a driver pinion and a follower gear. The gears are connected using frictionless contact. Note that the mesh is generated only on the contact regions because the geometry is rigid and not deformable. 2 Revolute joints are applied to the bores of the gears, allowing rotation around their local z-axis. We'll use the rigid dynamic system to model 2 intermeshing gears. The geometry is already prepared, but before running the analysis, I'll open it in SpaceClaim to review the model and create named selections for the contact regions. Since the bodies are rigid, there's no need to assign material properties unless we want to include gravity effects. We will define a frictionless contact for all gear teeth, so a surface mesh is generated only on the contact areas. 2 Revolute joints are applied to the bores of the gears, allowing each gear to rotate around its local z-axis. A joint load is also added to the pinion, acting like an actuator to rotate it during the simulation. Finally, we'll run a 1-second simulation where the pinion rotates 360 degrees and we'll observe the mechanism motion. That's enough explanation. Let's get started with the modeling. I'd like to analyze the mechanism of 2 rigid intermeshing gears, so I'll start by adding the rigid dynamic system. The solver is explicit, and since all components are rigid, we don't need deformation settings. First, let's import the geometry. I'll right-click on the geometry cell, choose Import Geometry, and click Browse. After selecting the file I created earlier in SolidWorks, I'll press Open. Before we continue, it's better to review the geometry. I'll right-click on Geometry again and select Edit Geometry in SpaceClaim. You can also use Design Modeler or Discovery, depending on what you're comfortable with. Now we're inside SpaceClaim, and we can see the 2 gears. The larger one is named Gear, and the smaller one is the Pinion. The bore of the gear looks too small, so I'll increase the diameter. I'll click on it and press P, or use the Push tool from the Design tab. I'll try 10 millimeters first. 20 millimeters looks much better. Next, I'll zoom in on the pinion bore, select it, and type 15 millimeters. I think 20 millimeters is more suitable for this size. These bore sizes are not real values for our simulation, and the exact dimensions aren't important here. Finally, I'll press Escape. Everything looks fine, but remember, in a real model, you should always use accurate dimensions. Now, let's check the distance between the 2 parts. I'll press E to activate the Measure tool. I'll click on the center of the pinion bore, hold Ctrl, and click on the center of the gear bore. The distance is 280 millimeters. I'll press Escape to exit the tool. In the next step, I'll define names for the contact regions, starting with the pinion. Since the teeth are in contact, I need to assign names to the pinion and gear teeth to define the contact regions in ANSYS Mechanical. To make the process easier, I'll use the selection tools. First, I'll click on the face of one pinion tooth and choose Face with Same Area. All similar faces are now selected automatically. I'll go to the Groups panel, click Create ANSYS, and name it Contact Pinion. I also need to include the topland of the tooth. I'll click on the topland, go to Selection, and choose Coaxial Protrusion. Then I'll return to Groups, right-click on Contact Pinion, and select Add. As you can see, all the pinion teeth are now selected and grouped under the same contact name. Next, I'll define the contact name for the gear. I'll click on one gear tooth and use either Equal Radius Protrusion or Face with Same Area. Then I'll go to Groups, click Create ANSYS, and name it Contact Gear. After that, I'll select the topland of the gear tooth, choose Coaxial Protrusion, and add it to the Contact Gear group. Now all gear teeth are properly selected and grouped. Everything looks good, so we can close SpaceClaim. As I mentioned earlier, the geometry is rigid, so we don't need to assign material properties in engineering data. I'll double-click on the model cell to open ANSYS Mechanical. We are now inside Mechanical. I'll press H to zoom to the full extent. Before starting the setup, let's check the geometry. I'll expand the geometry branch and click on the gear and the pinion. As you can see, both components have their stiffness behavior set to rigid. To keep things organized, I'll rename them. I'll right-click on the gear, choose Rename, and type Gear. Then I'll click on the pinion, press F2, and type Pinion, and press Enter. Now let's move on to the connections. I'll expand Connections and then expand the Contacts folder. The software has already created a contact pair automatically. I'll zoom in on the gear and pinion, and you can see that the teeth are touching each other. I have to assign the pinion and gear name selections that I defined earlier in SpaceClaim. I'll go to the details of the contact region and change the scoping method to Named Selection. For Contact, I'll select the Pinion group, and for Target, I'll choose the gear group that we created earlier in SpaceClaim. Now all teeth on both gears are connected correctly. Make sure the contact type is set to frictionless. If it was set to bounded, we would need to change it. In reality, gear contacts are frictional, but since our model uses rigid bodies, frictional contact is not available in Rigid Dynamics. Next, I'll generate the default mesh. I'll right-click on Mesh and click Generate Mesh. The mesh is created only on the contact faces. That's expected because the bodies are rigid. There's no deformation inside the volume, so only the contact surfaces need meshing. The element size is too coarse, so let's check the edge thickness. I'll click on the top land edge of a tooth, and the message shows about 20 millimeters. Clicking on the smaller edge shows about 6.4 millimeters. We need a smaller mesh size for better contact resolution. I'll click on Mesh, go to the Details panel, and set the global element size to 2 millimeters. Then I'll right-click on Mesh and select Update to regenerate it. After updating the mesh, the elements look much better. The element size is a bit too fine, so we can use a larger contact mesh. I'll change it to 3 millimeters and update the mesh again. A coarser mesh reduces computation time, which is useful for a tutorial example. Now let's move on and define the boundary conditions. I'll start by assigning a boundary condition to the bore of the gear. The best option is to use a joint. I'll right-click on Connections, go to Insert, and select Joint. I'll pick the bore of the gear and change the type from Fixed to Revolute because we want the gear to rotate around the Z-axis. I'll also change connection type from body to body to ground, and I'll set it to a mobile joint. Now, the gear will rotate around its local z direction, which aligns with the x component of the global coordinate system. Now let's define another joint for the pinion using a simpler method. I'll click on the pinion bore, go to the Connections tab, and select Joint. From the Joint menu, I'll expand Body Ground and choose Revolute. There you go. That's a faster way to define joints. The pinion will act as the driver and rotate the gear. To apply rotation, a joint load is the best choice. Before applying it, let's update the mesh. Everything looks good. I'll right-click on Transient, go to the Insert menu, and select Joint Load. In the Scope section, I'll choose the pinion joint. You may notice that the gear joint name is still incorrect and labeled as Fixed. To fix it, I'll right-click on the Joints folder and select Rename based on definition. Now both joint names are correct. Going back to the joint load, you can see that the selected joint is Revolute Ground to Pinion. This joint load will act as the actuator that drives the pinion. In the definition section, we can choose the type of joint load: rotation, velocity, acceleration, or moment. I'll select rotation. In the magnitude section, we can see that the simulation starts at 0 and ends at 1 second. I'll specify a 360-degree rotation over 1 second, starting from 0 at time 0. Everything looks good. The default simulation time is 1 second, but we can change it in analysis settings. The step end time is set to 1 second by default, but we can change it to any value we need for the simulation. The initial, minimum, and maximum time steps are fine at default values, so I won't change anything. To solve the model, I'll right-click on Transient and select Solve. The process takes a few minutes. Once the solution is complete, I'll click on Solution. You can see that the total simulation time was about 12 minutes and 51 seconds. Now let's visualize the mechanism movement. I'll right-click on Solution, go to the Insert menu, and select Total Deformation. Then I'll right-click on Total Deformation and click Retrieve this result. Let's play the animation and see the movement. I'll go to the Graph section and click the Play button. There you go. The intermeshing gears are rotating perfectly. To improve visibility, we can increase the playback rate. Let's try it. I'll pause the animation, set the frame count to 100, and play it again. As you can see, the motion is much smoother now. You can see the simulation timeline in the top left corner, and everything looks correct. This setup can also be used in transient structural analysis to investigate stresses and energy in the mechanism. That concludes this tutorial. Now you know how to model and simulate intermeshing gears in rigid dynamics. Thank you for watching.